getting into the importance of our spotters as we begin our SKYWARN training class and look at really the importance of this. And again, we're talking about building upon the principles of our SKYWARN training class. So certainly providing ground truth and being our ears and eyes on the ground is something that's really, really important with getting our spotters into providing that information for us and being able to provide some information about what's actually happening out in the field. So our detailed storm reports that we receive from our spotters can help us to verify warnings, allow us to add value to existing warnings that are out there, as well as lead to new warnings that are issued. We can also assist with post-storm analysis with those, get into research and assist local training efforts that are also occurring. And finally, it can mitigate some of those limitations with radar coverage. So you look at a given storm, and the radar is going to give us a lot of information about what occurs within that yellow box. So the radar is actually going to basically give us a lot of that detail with what's actually occurring within that radar. Radar range. So a lot of the detail with storm structure and the radar itself is going to be provided there. What the spotter is actually filling in is the material that's actually occurring below that. So basically the storm itself in the low levels, that detail is going to be provided by the spotter. So if you look at the 3D atmosphere, you'll have an area of low pressure here. We have a warm front out ahead of it, and the warm front will tend to, because warmer air is less dense than cold air. That warm air actually has to erode that cold air gradually. So it has to go over top of it and slowly weaken the cold air that's in place. So basically think about it as warm air slowly warming up the cold air that's in place. And that's a very gradual process that has to occur over time. On the back side of that low pressure, we have the cold front. And the cold front is the leading edge of cooler and usually less humid air. And as a result of that, that cold air actually pushes in, being more dense, will actually be able to come in and push that warmer air out of the way, which is going to be able to make that process evolve a little bit quicker, especially if that air is much colder and much drier than the air in which it's advancing on. So that cold air, if it's much colder, is going to be able to push through a lot faster than the warm front is going to be able to evolve. So here's your cross section of this, the warm front on the top, the cold front on the bottom. And again, it's a more gradual process with the warm front. The warm front's going to have to only gradually push through and modify that air mass on a very gradual scale. So it's a longer, it's a bit of a longer burn in terms of getting that precipitation and those thunderstorms through the area, because that's a more gradual progression. The cold front is usually a little bit more of a fast process, especially if it's a strong cold front. It can push through a lot quicker and basically just evolve faster, because that colder air is more dense and can really just push that warmer air mass out of the way, especially if it's much colder. Taking a look at your ingredients for thunderstorm development, and we talked about this in our basic class. The ingredients for thunderstorm development are moisture, instability, and lift, otherwise known as a convective trigger. So those are your three ingredients that you really need to have. That moisture sources all around us in terms of the bay, the ocean waters, the Gulf waters, providing that moisture, that additional humidity, those higher dew points. That's going to provide the fuel to get those storms fired up. The instability is the unstable atmosphere, providing the cooler air to provide those thunderstorms that can be fired. And the lift is the convective trigger, what's actually firing up those storms, be it a cold front or a gust front or an upper level trough that's pushing through. What is actually getting those storms fired up and pushing through? Now we have a question here. Warm air has to rise above cold air and eventually sink, while cold air can push cold air out of the way. Do I understand that correctly? Yes, that is the correct way to think of it, where basically the warm air has to actually push through and gradually warm up that colder air that's in place. So if you think of a colder air mass that's in place, a colder, more stable air mass that's in place, that warm air can push in, and only gradually can it warm the air up and get that more moist air mass pushed into the region. The cold front can just push through and knock everything through rather quickly. It's a more of an abrupt process. The cold front is a more abrupt process that can just push through and really get through the area rather quickly, especially if it's a strong front. The warm front is usually going to be more of a gradual progression. So good question there. So now some determining factors in terms of severity of storms is how unstable are we? And there are some ways we can determine that. And secondly, how much wind shear is available? And we're going to talk about wind shear here in a little bit. But wind shear is the fourth factor, if you will, in terms of providing the storms and what's actually going to be the storm mode. So stability is instability or stability, the level of which you are unstable. I basically would have to say that the degree to which vertical motion in the atmosphere is enhanced or suppressed would generally be a good definition of stability. So basically the amount of vertical motion that is present is going to determine whether you are stable or unstable. And depending upon the vertical temperature profile, that will be either air that rises or tends to sink or remain at rest. So how do we break that down? The unstable atmosphere will tend to want to rise, to lift with respect to air going upwards in the vertical. We kind of tend to call that a more cyclonic type of circulation, where we have a counterclockwise flow in the low levels, which will tend to foster or facilitate lifting or pushing of air upwards. So that's going to be supportive of convection. You need convection when you have warm air that is able to lift up and provide the beginnings of that unstable atmosphere. The stable atmosphere is going to tend to be what we call anti-cyclonic, or again, the opposite of cyclonic, which is to be supportive of high pressure. And high pressure will tend to want to sink. We call that subsidence. That's going to tend to be a drying process that allows the atmosphere to dry out rather quickly. So that stability will tend to suppress or resist the vertical movement of air. That's going to be a situation where you're not really going to be able to support a whole lot in the way of convection, because the air doesn't want to rise, it wants to sink. That's going to typically be when upper level ridges are coming in. We don't have the ability to allow that air mass to mix very well. It's going to want to push down and kind of push against any instability. Now, the more neutral atmosphere is kind of in the middle, as you might imagine. It's neither really suppressing nor enhancing the vertical movement of air, and you're going to therefore need to rely on other factors. So a lot of your low-level factors that tend to foster low-level mixing, that might be enough to overcome a neutral atmosphere, versus a more stable atmosphere where it's not going to be enough. The stable atmosphere is going to eventually win out in that respect. So let's look at an unstable atmosphere here and think of a given parcel of air. So we'll take an imaginary box of air, and we're going to take that imaginary box of air right around our heads here. We'll just take an imaginary box of air. So we'll say the size of a standard shipping box, let's say. And we'll take that box and we will imaginarily lift it up into the sky. And as that air parcel wants to lift or goes to lift, the air parcels will continue to rise. And as those air parcels rise, they will expand and get bigger. Now, as that continues, this will promote the formation of vertically developed clouds, which will eventually result in thunderstorms and tall smoke columns if we eventually have enough moisture in place. So if we have enough moisture, that's our first ingredient, and we have enough lift, that's our second ingredient, we will be able to foster a convective mode. So we'll be able to get clouds to start to pop up, those cumulonimbus clouds and those cumulus clouds that we think about in our schooling and our science classes, those cotton ball type clouds. As we start to get the air lifting and starting to rise, we can start to elongate them and stretch them in the vertical. And that's going to provide cumulus towers, which can result in thunderstorms that start to get rolling. In a stable atmosphere, that box is just going to kind of want to sit there. And it's basically going to kind of stay in one spot. So if you kind of think of a maybe a campfire smoke at night when you're first getting going right at night, that smoke's going to stay right near the ground and right on top of you. And that's going to be the kind of situation where, that smoke's not going to want to disperse and just going to want to sit there. And that's more of your stable atmosphere in that respect, where you're not really being able to mix that out very well. Those air parcels are going to be kind of stable and stay in spot. And as a result of that, not really supportive of lifting in this type of setup. Now, we have 4 different ways in which we can modify atmospheric stability. Number 1, for an unstable atmosphere, we can heat from below. So the sun will come out and it will heat the surface of the earth, and that warmth will rise off of the ground, heat the air around us, and allow that air to get warmed up by the ground. And that's a fairly typical way of actually getting our ground to heat, is the ground actually heats everything up for us. So the sun does all the work on the ground warms up the air, and the air then therefore rises. We can also cool from aloft. So if we have an upper level trough that comes in, as an example, we'll have that upper level trough move into the area, and that will provide cooler air that will push in from aloft. That's going to allow for cooler air to push in from the west, and that's going to tend to increase instability, because that'll allow for a warmer ground and a cooler air mass aloft. And as we can get that mixing going, that instability will therefore gradually get increased because of that difference between the cooler air aloft and the warm air at the surface. In the case of a stable atmosphere, we can cool from below. So basically we have, again, that cooler air mass that will push in, but if the air below is stable, that's going to enhance that stability rather than decrease it. So if you have stable air mass above and below, that's going to tend to resist that convective mode. Also, that would be in the case of warming aloft. So if we start to have warmer air or ridging coming in from aloft, high pressure coming in aloft, so an upper level ridge comes in, that warmer air at the surface and the warmer air aloft are going to get along pretty darn well, and it's not really going to be conducive for a lot of lift because the air temperature difference is going to be lower. So there's going to be less instability because those air masses are going to be in more complete alignment. This gets us to the concept of a temperature lapse rate. And the temperature lapse rate is basically the expression of the instability versus of how warm it is aloft versus how cold it is how warm it is at the surface versus how cold it is aloft. So basically, this time of year, in the spring and into the summer, you're going to generally start to be warm to hot in the lower levels. The instability is going to come into play when we look at how cold it is in the mid and upper levels of the atmosphere. So generally, the cooler it is aloft, the higher and more steep that lapse rate is going to be. And the lapse rate is basically the expression of how different the temperature is in the upper levels versus the lower levels in downstairs here at the surface. Typically, the more instability you have, the greater the difference is between the temperature aloft and the temperature at the ground. So this time of year, in the warm season, you're going to be most unstable when you're hot, very warm to hot in the low levels and cooler aloft. In the winter months, you can still have instability and you can still have severe weather, but it's going to be, again, a factor of how cold it is aloft versus how cool it is at the surface. If we have relative cool air in the low levels and it's cold aloft, you can still have a very steep lapse rate, which will result in instability being higher. So basically, your change in temperature over your change in altitude is going to be your lapse rate. So how do we measure that? How do we quantify lapse rate? Well, we use the radiosonde, which is done not at our office here in Wakefield, but at all of the area forecast offices surrounding us, and including the flight facility out in Wallops. And that is basically through a weather balloon that gets launched twice daily. And those balloons will go up and measure that temperature all the way up from the surface to 100 millibars, which can be 100,000 feet up into the air. And that will give us the forecast sounding. So the forecast sounding is a way to take a picture of the atmosphere with respect to the temperature and the dew point and the moisture content and the wind direction and intensity. And how we use that is looking at the sounding, which is what you see here. This is what we call a skew-T diagram. And the skew-T diagram measures the temperature, which is the line to the right here, and the dew point, which is the line to the left here. And we can measure what we call convective available potential energy, or CAPE, to determine how unstable we are. And generally, as you go from the center of the screen to the right here, you're going to increase temperature. As you go from the bottom to the top, you're going to increase the height or the level in the atmosphere. And you see the elevation in meters here. So in general, your flight level is going to be generally right in here. This is where your planes are going to fly, down in here. This is the low levels of the atmosphere here, about 850 millibars. Your flight level is going to be in here. And then the far upper levels are going to be here at the top. This is upwards of 1,600 meters up. So this is quite a ways up, 100,000 feet up. So quite a bit of elevation up there. When you look at the reflection of this skew-T diagram, you can start to get a feel for the convective available potential energy, or the amount of instability that you have to play with. And this is going to be a determination of how much instability you have to play with. And this is going to be your CAPE right in here. And the profile of this CAPE, whether it's tall, short, skinny, fat, that's going to determine how much instability you have and what kind of instability you have. And again, you're going to start to notice that box in the lower levels. That same box of air is going to expand as it goes up, because that air is going to want to expand as it goes up into the atmosphere. So that same box of air is going to expand as it goes farther up into the sky. And that's going to be important because that affects our instability. So let's look at the shape of that CAPE. And we talked about the equilibrium level in basic. And the basic equilibrium we talked about in basic SKYWARN, the equilibrium level is going to be the top of our storm. And the lift will continue until we get to a point where instability goes away, when instability goes back towards a neutral atmosphere. And that's going to be what we call the equilibrium level, and that is EL for short. So in a case where we have weak CAPE, or rather skinny CAPE, this is going to be a lower storm potential, a weaker lapse rate, so less of a difference between the temperature aloft and the temperature at the lower levels. Typically, we'll measure at 1,000 millibars, so right at the surface, or basically sea level, versus 500 millibars, which is a proxy for flight level. So that's a proxy for looking at what the temperature and what the airflow is in the upper levels. And I do see a couple of hands up. I will go ahead. Feel free to ask the questions, and we will ask the questions or answer the questions as we go. So I do see the questions in there. If you have any questions, feel free to use the questions feature for that, and we can answer those as we go. But as you look at the weak storm potential in here, you can tend to see that this is, because of that weaker lapse rate, you're going to have lesser lift, lesser amounts of storm potential in here. So the equilibrium level is going to be lower to the ground. So you can see the Cape. We have a question, can you see Cape? And we do have a couple of slides here where you can actually see Cape. You can visualize it. So we're going to get to that. Basically, the most direct answer is you can see clues. You can see context clues looking at the sky, and you can spot. But typically, if you look at soundings, you can get a pretty good idea of what the Cape potential is going to look like. Now, in the case of a more fat Cape, or a larger amount of Cape that is available, this is a higher storm potential. There's a steeper lapse rate. There's more available potential energy available to get this upwards and lift it upwards. So you see your Cape is higher, and then the low Cape example, the equilibrium level is higher than in this Cape example, and then you have more Cape that can lift higher. More Cape will tend to want to lift higher. And in this case, your equilibrium level, or the top of your storm, is going to be at about 12 kilometers. So this is going to be a ways up. This could be 40, 50,000 feet up at the top of our storm, versus this might be more 25 to 30,000 feet. So again, that's going to make a big difference in terms of lift. Now, in terms of basically the Cape itself, this is only one ingredient. It's not going to be the end all be all. There are lots of different variables that we look at to make an accurate forecast here, but this is one of the more simple elements to classify, and something you'll see us mention in our forecast discussions fairly often. Now, taking a look at whether you can see, we had a question about, can you see Cape? Well, the best way to see Cape is to look at a sounding. But if you want to see Cape visually, looking outside, this is a good way to look at it. And this is a rather sharp anvil that you can see here in this picture. This is a case of a really strong updraft. This is a very crisp anvil. There's a very high amount of resolution difference, or a very strong contrast between the sky around it and the anvil itself. This is telling you have a very strong amount of lift that is available, a very strong amount of Cape that is available. And we're going to have more shots here and more contrast here as we go. Now, the fourth ingredient. Now, I told you about moisture, instability, and lift as our three ingredients for storm development. The fourth ingredient, or 3B, if you will, is wind shear. And wind shear is the change in direction with speed and with height. And here's an example of the both of them. This is speed shear on the left. This is simply increasing wind direction with height. This is changing your wind direction with height. This is changing direction with height. This is changing speed with height. And the strongest, or the best setup for severe weather is when you have both of them present at the same time. So you're increasing the wind speed with height, and you're changing the wind direction as well. So both of those present will tend to be more supportive of severe weather versus having one or the other. So why does this matter? Why does wind shear matter? Well, basically, if you have at 10,000 feet, a nice 60 mile per hour wind jet coming in out of the southwest at 60 miles per hour, that is going to allow our storm to tilt a little bit, so we can keep the updraft and the downdraft separated from each other. Aloft, you might have 40,000 feet, 90 mile per hour out of the west or northwest. That's going to provide that push at the top of our storm to keep that outflow moving. So that's going to keep the updraft and the downdraft separated. That's going to allow that storm to keep refueling. We talk about moisture, instability, and lift. That only works if the updraft and downdraft are separated from each other. So in terms of getting our storms to develop, if that updraft and the downdraft are working against each other, that's going to create a net neutral or a net negative, which is going to allow that storm to pretty much just die out. If you have this situation where the updraft and the downdraft are separated from each other, that's going to be supportive of storms continuing. So again, here's what it kind of looks like in visualization. A more weak setup is going to be the downdraft choking off the updraft, which causes the storm to be short-lived. If in a more strong or idealized scenario, you're going to have the updraft set up and able to keep the updraft and downdraft separated from each other. So this is the updraft in a weak wind speed or wind speed shear setup. So basically the airflow is going straight up. And as the result of that, you have a minimal amount of shear present. Let's make this a stronger wind shear setup. So we're increasing the wind with height. So we're increasing the winds aloft. What that's going to do is it's going to provide a bit of a stronger flow aloft, such that the updraft or the airflow is going to tilt in the vertical. When this happens, you're going to tend to allow our storms to slant a little bit in the vertical towards the updraft. So the updraft is able to go up and keep the storm separated from the updraft to the downdraft. So that's going to allow our storms to continue to move. I have a couple of questions here. Is this presentation being recorded and will it be posted on YouTube? Yes, it will be posted, and we're going to have this on our YouTube feed shortly. We do have last year's show also on there presently, and the handouts are going to contain the PDF of this class. So you can download those from your handout section, or you can simply wait for the email. It's up to you, your choice. I have another question here, which I can't really make out. Can a person do the job if there are no cars? I'm not sure what that is. If you can ask that question again, I'm not sure what that is. So the slides are going to be available. The slides are available presently, and they will be made available via email as well. So for those who are taking the class live, by all means, those will be emailed to you. The question I had is, can a person do the job if you have no car? This is something that you can do certainly just spotting and looking around. So this is not something that requires chasing by any respect. This is something that, we're just looking for our spotters to report simply what you're seeing at your location. So this is not something that you need to drive around for. In fact, we don't want our spotters to be going around chasing for the most part, unless they very much know what they're doing with this. So it does bring a little more element of danger if you're driving around chasing these, because storms are very capable of changing directions quickly. So no driving around required. So we'll go ahead and send those handouts to you. We'll go ahead and do that. So you're going to get the copy of that. You can also download them from the website as well, weather.gov/Wakefield. You can download the advanced slides from the site directly. But we'll have those sent out to you via email as well for those who are completing the class live here. For those who are watching virtually or after the fact, they're going to be posted to our website at weather.gov/Wakefield. Okay, so back to this. Again, if this is tilted, you're going to be able to watch these start to lift up, and the updraft and downdraft will be separated from each other, which is going to allow the storm to continue to grow. So the updraft will bend the air turning upward, and that's going to tend to provide the spin with the wall cloud in the updraft area. So basically that rotating column of air that we talk about as being the precursor to the shelf cloud in the downdraft section as the gust front or the shelf cloud. As it starts to get tilted into the updraft, it's going to bend that turning column of air upward, and that's going to tend to create the beginnings of our wall cloud, and that's going to create that beginnings of our funnel or our tornado within the wall cloud area. So when you have enough wind shear, that's quantified using terms like helicity and bulk shear. So we can basically quantify how much shear is available by using what's called storm relative helicity. And that's something that you can absolutely start to look at on mesoanalysis and start to look at. So with the rotating updraft, you're going to have that column of air start to get tilted into the vertical. When you have a supercell, you're going to be able to take that tube of air and start to lift it up into the vertical. So it's basically the same ingredients as a basic thunderstorm, but you're adding that speed and directional shear component to kind of take that tube of air and lift it vertically to the point where you have that wall cloud now showing that rotation all the way up into the cloud vertically. So your updraft is going to go back upwards towards the overshooting top here at the top. And that's going to be your updraft area. So when you see this overshooting top, that's telling you you have a strong vertical velocity. And again, you can look at the mesoanalysis from the Storm Prediction Center to kind of quantify where that stronger helicity is, where that stronger the 0 to 1 storm relative helicity, as you can see here, that is your cue and your key for areas that are conducive to the development of potential tornadoes or tornadic activity, is where you start to see these higher SRH values start to develop. So it's measured at several different height levels. This is going to aid in determining the storm type, or convective mode is a typical term that we will use. Convective mode is a kind of a synonym for what kind of flavor of storms we're looking at, if you will. What are the storms going to tend to be predisposed to do? So 0 to 6 kilometer wind flow, we're going to tend to get into storm motion. Which direction of the storm is going to be moving in? Are they going to be moving west to east, northwest to southeast, etc.? That's going to be a pretty good idea of where we expect our storms to be moving from and towards. 0 to 3 kilometers is going to give us a pretty good look at the storm type. Are we looking at more single cell type convection? More linear, more supercellular? What kind of storm mode type are we looking at? So that 0 to 3 is going to give us a lot of clues on that. And 0 to 1, as we talked about here, that's going to tell us how well formatted we are toward the development of tornadoes. Again, the higher this SRH value is, the higher the 0 to 1 shear is, the more predisposed we are towards the potential for tornadoes. And again, the links that you see there are going to be your way to classify that. spc.noaa.gov is going to have a lot of this information. And then the mesoanalysis, which is available on their website, you have a good way of actually looking into this, and you can watch this in real time along with us with respect to what is actually going on out there. So we talked earlier about, do you need to be able to see this? How can you see it? And this is a good way to actually visualize what's actually going on with respect to the upper levels. So you can look at the overshooting top. The overshooting top here is what we would call like a little hat or a cap that's kind of overshooting the anvil. And this is telling you you have a strong vertical velocity, a strong updraft. What goes up is going to continue to go up until that instability is actually going away. And when that instability goes away, it tends to make its way back down to the ground towards the downdraft area. But if that updraft is in a situation where it's going really fast and it's a very strong vertical velocity shooting upwards very, very quickly, it's going to get to the top of our storm, our equilibrium level, and it's not going to be able to stop in time. So it's going to get to that equilibrium level and it's going to bust through it. Think about breaking through a glass ceiling or breaking through blacking through the top of a building. That's going to be what you would think about with the overshooting top, is the air is going through so fast that it gets to the top of our storm that it just can't stop and it's going to bust through. And when it does so, it's going to create this overshooting top. When you see that, that's going to be a thick cumuliform anvil. It's going to be a very sharp contrast there. And you're going to be able to see the anvil right at the front. Now the anvil is going to be typically our meteorological neon arrow. So it's going to be able to tell you which direction the storm is moving. With respect to our stronger storms, you're going to notice the main tower has a cauliflowery type look. So you're watching the storm itself. Right in here, you can start to see that there's more of a cauliflowery type look to these storms. So there's going to be more of a stronger lift that's going to be evident. So the presence of the flanking line is going to be more conducive of storm organization. So you're going to be able to look at storms that are more organized and stronger. So down here at the bottom, you can start to see, really some clues that our storms are more organized. Now on the low levels, if you're watching our storm starting to develop, you can see our typical setup with respect to a supercell. You have your rain-free base here on the right that I'm circling. You have the updraft area over to the left, and you can start to see the downdraft area on the backside, and you can start to see the wall cloud here in the foreground to the left. That's going to be your supercellular environment. You can see the downdraft area is going to be the darker area with the heavy rainfall and the potential wind, straight line wind. You're going to see your rain-free base in the updraft area. Where they interface or where they come together is where your favorable location is going to be for severe weather. So where that comes together is where that tends to be where the strongest storms are going to be. This is where you'd be looking for rotation as well. So this area is where you'd be searching for that rotation to be. So that wall cloud is going to be, again, the abrupt lowering of the rain-free base at a spot. So you can start to see the spots kind of showing right here in the wall cloud, and you can notice the rotation there. Now, again, with respect to spotting, the funnel cloud is not going to be in contact with the ground. So if you have a little protrusion coming down in that wall cloud area moving towards the ground, if you're seeing impact with the ground in terms of debris getting kicked up, in terms of damage being done, that is the tornado on the ground, not the condensation funnel itself. The funnel cloud is going to be if you see that protrusion, but if you don't see anything going on at the ground level. So nothing in terms of debris getting kicked up, nothing in terms of damage being done. That's going to be how you would tell the difference whether there's actually something happening there, rather than focusing on the condensation funnel itself. On this side here, you might see some clouds kind of rotating, or not rotating, but kind of floating through space, doing its thing, not really bothering anybody. This is what we call scud clouds. This is what we call the scary looking clouds that we've referred to in basic. These are clouds that are what we call convective debris. They're not bothering anybody. They're not really doing anything. They're just kind of sitting there. That's really what they do. They're not really doing anything. They're just kind of sitting there and being scary looking clouds. So the wall versus the shelf. On the right there, we have our shelf. It's going to be on a lower horizontal axis. So you're going to be able to see this more across. The breadth would be across. And the wind is going to be outflow coming from underneath the clouds towards the person that's taking this picture. The wall cloud is going to be a vertical extent. It's going to go upwards in the vertical. It's going to be an indication of lift, so along a vertical axis. Now going back to the strong or weak updraft, you can start to see here, the stronger updraft, you're going to be able to see this really sharp, bubbly looking towers with a more cauliflowery look. This is telling you have a strong amount of vertical velocity going up, pushing these clouds upwards in the vertical. You're going to have a really sharp contrast to the clouds. Versus this is what we call more of a weak updraft, because you can start to see the fuzzier clouds. You can start to see the contrast here is a little more smoothed out. Like you take a picture and you hit smooth a couple of times. This is more of a smoothed out picture. It's not as sharp. It's not as contrasted. The parts are more translucent. The edges are not well contrasted. So it's more of a weaker amount of updraft. The shell for the wall cloud is going to be the lowering of the rain-free base. If there was video here, you'd be able to observe rotation within this picture. So you're not going to be able to see a whole lot of detail here. So if we get this down, you're going to be able to see a rotation occurring here. So let's look at storm type real quick. You have a multi-cell cluster on the left here. This is downburst winds, maybe some hail, some flash flooding potential. The tornado potential is typically going to be fairly low in this type of a storm mode. So it's going to be fairly low. The multicellular bow echo, this is going to be something that will almost exclusively be damaging winds, especially here at the apex in the center. You think of it as draw a bow and arrow and drawing the bow and arrow back at the apex or leading edge of that bow. There's going to be some stronger winds there. You can see some weaker echoes within that bow. That's what we call an inflow notch, where we start to see some rear inflow, some wind kind of peeking in and pushing into this line, where we start to get some indications where some stronger winds are evident here. So this is damaging winds that are going to be evident within that apex. There's the potential for some isolated tornadoes. They are going to be fairly weak, and they're going to be short-lived, usually, because this storm motion is usually predisposed to moving through pretty darn fast. So you're going to have some isolated tornado potential, but it's going to be predisposed primarily to damaging winds. Flash flooding is possible here, especially if this line is moving slowly. But this is, again, something that will tend to be more progressive and is not always going to be something that'll produce flash flooding unless it's training or moving over the same area multiple times. Hail is usually going to be low. Once again, these are moving through pretty quickly. Now, with the supercell, this is going to be pretty much all modes of severe weather possible here. So tornadoes, large hail, damaging winds, flash flooding, the whole enchilada is going to be available with our supercell. All modes of severe weather are going to be possible. There's enough shear, there's enough lift, there's enough instability to create pretty much any hazard here. So all hazards are on the table with the supercell. Now, in the online format, this is where we would take a break. So feel free to take a break where you are. We're going to continue on with our training. And we'll talk about radar. And the radar is radio detection and ranging. And radio detection and ranging is basically the weather radar using basically sound to determine what kind of targets are going on around it. So those pulses are going out from the radar looking for hydrometeors, which rainfall, raindrops, snowflakes, hail, which will end up hitting insects and dust and things that are in the air around us. And the radar is going to pick up all of that in the form of clutter, in the form of precipitation. All of that's going to be evident when you look at a radar slice. So those pulses are produced at multiples per second. In between those pulses, the radar is in listening mode. So it's listening for that signal to come back to it, which is why we call it an echo. The radar is listening for the return of that signal. And the amount of the signal that gets returned is the reflectivity. That's how we know that there is something going on out there, because that signal gets returned to the radar. If there's rainfall out there, or a lot of something out there, the radio or the radar is going to receive a lot of that radio signal back. A lot of that signal that it pushes out is going to get pushed back to it. It'll bounce back to the radar, which is why you receive those high reflectivities in an image like this. So the higher the reflectivity, the higher the colors, the oranges and yellows and reds, the heavier the rainfall in that area. So the colors are used to display low and high reflectivity. The hotter the color, the higher the reflectivity. Always use the legend when you're looking at a radar to see what the high reflectivity is versus the low. So while it can pick up, the radar can pick up birds, insects, leaves, debris, anything that it can pick up. We primarily use the reflectivity slice to pick up heavy rain, snow, precipitation in general. Now, the Doppler effect, we hear Doppler radar all the time. That is, the Doppler effect is a change in the frequency of a moving object. So the targets moving towards the radar are going to be colored in green. So as we look at the velocity slice, that's going to be something where airflow moving towards the radar is going to be in the green. Moving away is going to be in the red. Where we have the potential for tornadoes is when we have a couplet. So intense inbound winds next to intense outbound winds. So the brighter the color, the stronger the wind. We can see tornado circulation potential in areas such as this. And as we zoom in a little bit more, this is where you would get a more detailed look at the circulation. And this is a very strong tornadic circulation that is evident on the radar. So again, the dual polarized radar, which we've had for more than a decade now, provides a 3D look at our storms. So it's putting pulses out in the vertical and the horizontal and allows us to see the size and the shape of the weather around us. So it allows us to look at how large the hail is, how large the raindrops are, how much wind is available to be seen. Now, if you look at the correlation coefficient, and this is one of our derived products from the radar that is available for interrogation. As you look at the full breadth of our products on the radar, it's the correlation between the reflected horizontal and vertical power returns. So basically, it's a good indicator of hydrometeor diversity. And what that means is everything. We'll take the example of a box. Take a box in the atmosphere and push that up to where our storms are. If you look at if you look within the contents of that box and everything were to be raindrops, you'd have a high value of correlation in there. Those would all be raindrops. So that's a very high correlation. Is to be closer to 1. A very high value of correlation, you'd have a very high correlation of basically entirely raindrops. Now, if you look at that box and you see, well, we've got some hail in here, and we've got some storm debris in here, and we've got some high, some very large raindrops and some very small raindrops. That's going to be a very low or a lower correlation coefficient because there are lots of different disparate things in that box. So typically, when you get into more disparate things within that vertical box, you're going to start to lower the correlation coefficient. And we're going to talk about more about that in a couple of slides here. This gets into the limitations of our radar and talking about how resolution decreases with distance and the curvature of the Earth. Because of that, we need a network of radars that's working with each other. As a beam goes out, as the radar beam goes out from our radar here in Wakefield or wherever else you're watching this from, our radar, as it goes out, is going to spread over a larger area the farther it gets away from the emanation point. So when that beam spreads for nearly 1,000 feet for every 10 miles of travel, at 60 miles, you're seeing about 6,000 feet wide. So you're looking at about 6,000 feet wide. By about 120 miles, which is the outer the outer edge of our radar coverage, you're going to be looking at more over 2 miles wide. So that's going to impact the resolution capability of the radar. What that means is you're going to get a less reliable and less informative radar slice the farther away you get from our radar. So we'll start to build this up. Say 25 miles away, you're looking at our radar at a supercell, and you can see some pretty good detail in the low levels. You can see the hook in here. You can see a little bit of the forward flank back in here. You can see a little bit of the inflow here. A lot of good detail here at the radar in the lower left-hand portion. Let's go to the upper right-hand portion, 94 miles away. You can still see a lot of that structure, but the details are a little bit more fuzzy. So you're losing some of the detail there. And you're getting a lot of the same information, but it's a little bit less discrete, a little bit less able to be filled in. We'll go a little farther away, go to the upper left And you can look at this radar here that's sampling at 11,000 feet, 112 miles away. And again, you're starting to lose a little bit more of the structure. You're going to start to lose a little bit more of those details. And it's a little higher up in the atmosphere. So you're starting to lose a little bit more information here. And then finally, we'll go to the lower right-hand portion, 167 miles away, 21,000 feet up. And again, you're just seeing a blur. It's more of a general reflectivity versus getting more detail in there. So we're losing a lot of the real detailed information that we got in those lower levels, and we're higher up and we're getting less detailed information. So again, the farther away from the storm you're getting, the less information that you have from our radar that's going to be able to give you more detailed information. So let's look at our storm structure for reflectivity, and this is the idealized example of storm structure and reflectivity. And again, you can start to see the low pressure would tend to be at the confluence of the updraft, or the forward flank and the rear flank. This is what we would call the occlusion area at the center. You would tend to have the rear flank downdraft coming in and pushing that cooler, drier air in from the backside. So this is the cooler, drier air coming in. This is the straight line wind, the shelf cloud coming in on the backside. On the forward flank, you're starting to look at the warm front on the leading edge. This is where you're going to have all the, you're going to start to have all of the rainfall in this area, in the forward flank. This is where all of the forward flank is going to have all that heavy rainfall. So right in the middle is going to be where that inflow is going to be. Let's go back to... There we go. So you look at the overshooting top and the striations in the anvil. That's going to be right on the leading edge there. So the most likely area for damaging wind, large hail, and tornadoes is going to be right in this area, right in here. I'm going to erase all ink there. There we go. So we're going to overlay our radar, and again, the tornado is going to be right in that area, right at the confluence of the low pressure, right there. So your tornado is going to be most likely in that area. In terms of velocity, we're going to be able to look at that, and again, you can see the red, or the pinks, the warm colors, that's going to be airflow blowing away from the radar. So this is going to be blowing away from the radar. So this is your airflow blowing away from the radar. This is your airflow blowing towards the radar. So this is going to tend to be your airflow blowing this way and then going back this way. Your radar is going to be back in the upper left. So you're going to start to see that circulation is going to be your circulation around the tornado right there. Now with the dual polarized radar, what we can actually do is we can overlay, let me turn off my ink here. Okay. And then you're going to be able to look at the correlation coefficient. Now, we talked about the correlation coefficient before as what's going on within that bin, what's going on within that box. And within that box, within the tornado itself, you're going to start to see a lot of disparate things within a given box, within the updraft, and that's within that tornado. Now, that's going to be the precursor of tornadic debris. So if we have a tornado in there, there's going to be tornado debris that gets kicked up. So siding or whatever debris gets kicked up from the surface is going to get wafted upwards into our thunderstorm. And that's going to show up as what we would be within that correlation coefficient. Now, again, we can't use the correlation coefficient to be the diagnostic tool for tornadoes, because obviously with respect to tornado debris, if we are looking at radar to determine that there's tornado debris, you've missed the tornado beginning. So we can confirm that a tornado has occurred with respect to tornado debris. That's why we call it a radar confirmed tornado. But in terms of actually diagnosing the radar from the radar itself, we need to look at that velocity and figure that information out before that actual look at the correlation coefficient shows up. So as far as the radar itself goes, the radar is going to provide you a lot of really good information. So find a radar that you like and you know how it works. There are lots of different types of radars out there, products. There are paid ones, there are free ones. Whatever works well for you is going to be the one that you can use. My advice would be to have as many as you can have on your device as possible safely. You don't want to contain like 30 or 40 or anything like that, but have a couple or 2 or 3 that you like and can use because these software items tend to fail at the worst possible time. So find an interface you like and know how it works ahead of time before the storms come in. If you are mobile, if you're out and about and you're looking at storms, use something that you can place your current location in. So figure out where you can determine, hey, here is where I am. Here is where the storm is. Try to figure out the difference between the two and something that will determine where you are versus where the storm is. If you're not sure, have as many different things as possible. So again, have a couple of different radars that you like and can use because if one fails or decides to stop working for that day, you have another one that you can use. Now, in terms of impact-based warnings, these are a product that we've been using for several years now, and they will be appended at the bottom of tornado warnings and severe thunderstorm warnings and give you information as to what we are basing the warning on. So you can look at the tornado tag to kind of figure out whether it's radar observed or whether it's something that has actually been seen out in the community. So somebody that has actually seen a tornado. That's going to be a higher level of threat, obviously, versus a tornado that is radar indicated only. If we have something that is confirmed by the radar in terms of seeing that tornado debris being lofted, that can be called a radar confirmed tornado. That is going to be provided here as well. Now, we have the ability to append damage tags to our storms. These are going to be based upon larger hail, and we're going to base that on tornadoes as well. We'll be able to have that in the next slide here. We can talk about here, we'll look at the impact-based meteorology and basically looking at newer radar technology and products that can affect our decision making. So there's always going to be new products out there, right? So we're going to always be looking for what's available that can enhance our decision-making process. For social science, the idea is for small wording changes and warnings to make things a little bit easier to understand, to make things as clear and concise as possible, to limit confusion as much as possible. And finally, for our friends in the media and for the general public, we're looking to key in on the most important aspects of the warning. So that's why we're doing that. So in terms of the considerable tag and the destructive tag, these are going to be appended, like I said, to our warnings and a base, quote unquote, base warning of 50 to 70 miles per hour, 1 to 1.5 inch hail in diameter is not going to be a tag. It's going to be a basic warning that's out there, no change from previous method. A 70 to 80 mile per hour wind speed we're expecting, golf ball to tennis size hail. We can call that considerable threat. So basically something that will provide a considerable threat to life and property, no change there. If we are expecting baseball size hail or greater, 80 mile per hour winds or greater, we can tag that as destructive. So something that can alert as a WIA on your phone. So when you think about the WIA alerts, that's going to be that alert that goes to your phone directly, that turns your phones on and starts to send off those alarm types. That's going to be sent through your web carrier or your cell phone carrier and give you that WIA alert. Now, in terms of storm surveys, this is a historically and traditionally Weather Service role, something that we in the National Weather Service do on a regular basis. We may not, in a lot of cases, have enough staff in the case of a large event, a large scale event like Isaias or the outbreak of 2011, or something really, really big in terms of widespread damage that's getting done. We may not have enough resources to provide storm surveys to everything. In those types of situations, we have emergency managers and sheriff's deputies that can go out and accompany us on surveys. So we can basically allow them to go out and look at the damage in their communities for themselves and report back to us, and allow us to get that information and get a first look assessment from them with the idea of here's how we can provide more information down the road. So when we look at storm surveys, the first thing as a storm survey team that we're going to ask is, what do I focus on when I arrive at the scene of damage? So we don't focus exclusively any longer at what solely has been destroyed. It's simply looking at considering what wasn't destroyed and how things were damaged to provide context. In the case of storm surveys, the most intense damage usually occurs over a small portion of the damage swath. So in the case of an EF5, we might only have 2% of the worst damage occurring within that area. So it's only going to be a small area that the worst damage is going to occur. So a weak tornado entering a community might do its worst damage early on when it's first developing, and then as it weakens, it will do gradually less damage. Whereas a stronger tornado is going to produce a large debris load. So it's going to be interacting with structures that damage could increase as it gets farther into the community. So basically, whereas a weaker tornado will weaken on its path, a stronger tornado will be rather consistent and do its weakest damage in a very significant or in a very strong area of damage. Now, in terms of tornado or microburst, we typically will have folks who will report damage, and when we say that your damage was, consistent with a microburst, they tend to take offense at that, and that's not something that we're intending, certainly, because really a tornado versus a microburst is really just the question of converging versus diverging wind speeds. So if winds come together over a damage path, it's going to basically provide damage on one side of the path versus not on the other side of the path. That's consistent with a tornado. That is when you have damage on one side of the street and little or nothing on the other side, potentially. A diverging damage path is going to be a more large scale damage path. So basically something where our airflow is predominantly fanning out. So the damage path for a tornado is long and narrow. A microburst is brief in duration and farther out. So the more divergent damage path is going to spread out. It's going to knock down everything in a fairly effective fanning out pattern. A convergent damage pattern is going to be more chaotic. You're going to have damage on one side and not on the other side. You might have one side of the street fine. You might have one side of the street sustaining heavy damage. That's going to be consistent with a tornado. Again, see this field, there's damage toward the middle of that picture going across the pattern. In the center, there's damage. On the left, on the right, there isn't. That's a convergent damage path. So in terms of what to report, these are basic information about measured estimated wind speeds. So if you can measure wind speed with an anemometer or an automated weather reporting sensor, an anemometer, you can use that. Use the automated weather station information to report that damage. That's going to be more reliable. If you have wind damage, you have damage. So trees down, power lines down, tree limbs down, damage to vehicles, stuff of that nature. That's going to be reportable. Tornadoes, waterspouts, that's going to be reportable. Funnel clouds, significant flooding, hail of any size. If you have hail, report the largest size of hail that you have. Now, there are lots of different ways to report. You can report to your favorite television meteorologist. And we're not discouraging you from doing so. But if you do so, realize that they may take a couple of minutes to a couple of hours to get that information to us. You may call to your county or your non-emergency number, and that will go through emergency services eventually to us in a roundabout way. You may report to your fire department or the emergency manager. That will get to us in a roundabout way. You may report in other mediums that eventually get to us. But realize that multi-level communication is going to be slower, and it's going to result in a misrouting potentially of that information versus sending things directly to us through these measures, through these avenues, sources, sites, is a way to get this information to us directly. So through our website, we have a place that you can send information directly. This link on the bottom, weather.gov/AKQ/report weather, that's a way to report online. You can call us directly with our phone number here, and that's going to get us our information quickly. You can call us directly any time of the day or night, and you can get our storm report information sent to us directly. If you have reports, you can email us at akq-report@NWS.gov, and you can get pictures to us or send reports to us after the fact if you prefer. The only thing I'll say is if you have something time sensitive, to go ahead and report via phone if you possibly can, because that's going to be something that's most time sensitive. That'll get us our information faster. And then finally, through social media, Facebook or Twitter or X or whatever you call it, get that information to us as quickly as you can via those medium as well. For those who are looking for a completion certificate to this, you would use the password SKYWARN 2025. That's going to be sent to you via email as well. You can register this as your name and your training date, and you'll get this certificate that you can use for your purposes, for continuing education credits if you like, or just for your reference, for your records as well. You can be used to have this information for your purposes. Realize you may be infrequently contacted for severe weather reports. We are almost never going to contact you because we don't know whether you're watching the weather or out of the area or just not looking in general. So we're going to tend not to call you, but realize if you are on our spotter rolls, we might call our spotters to ask, what are you seeing? What's going on in your area? So this is our last slide here. Feel free to use our QR codes here to download our field guide, our spotter guide here on the far left, our website here. Our numbers for being reached here on the bottom is down at the bottom. If you have any questions, feel free to email us. And thank you very much for participating here today. We very much appreciate it. I'm going to go ahead and answer some questions. If you are watching a recording of this, feel free to send any questions to AKQ Report or these emails here on the right-hand side. Thank you so much for participating today, and it's great having you as part of our team.